After the raster data model, logically we're moving into raster analysis, and that's the focus of this lecture topic. We'll start with things that are relatively simple, map algebra, move into logic-based analysis with Boolean types of functions, and then we'll end out with local, focal, and global types of operations that work on raster data sets. At its heart, map algebra is simply applying functions on a cell-by-cell basis to our input raster grid or grids. There are a number of different functions that can be applied and used here. One of the critical elements, as with any type of raster analysis, is that the rasters, the grids, must line up and match with both vertical alignment, if you think of them stacking one on top of the other, meaning that the cells must align perfectly with or between different grids if we're combining them in some way. Okay, so using the two examples here, on the left is an example of applying an operation multiplying the input grid by 2. So every single cell gets multiplied by 2. The example cell in the figure, if we take 3 multiplied by 2, we get 6, and that's in our output grid. So this is applying an operation to a single grid. The example on the right is if we have 2 input grids, A and B, and we simply add them together. We add the values together. So it's layer A plus layer B, raster A plus raster B, however you want to think about it. But the mathematical operation takes each coincident cell between the two, and this is where that idea of a stack kind of comes in. If they stack, you can like put a line down through them all, and in this case, every 2 cells that are coincident between the 2 layers are added together. So that upper left-hand corner, 2 plus 1 equals 3. So this is how map algebra functions, using single input grids, or in some cases many multiple input grids, applying operations between them. But the key thing, the element to remember, is that, well, the cell sizes need to be the same. The projection systems need to be the same, ideally, and that each cell lines up with its matching cell perfectly in order for these things to work. Here's an example of map algebra doing a unit conversion, which is something we quite often do. If we wind up with data in one unit that is not what we want, and we want to convert it to something else, so we just apply map algebra. On the left, we have precipitation for a raster measured in centimeters, so 1998 centimeter or precipitation values in centimeters. We really would prefer inches because, of course, we live in the US and no one knows what centimeters are. So we apply the appropriate conversion to the variable. Precip centimeters divided by 2.54 gives us 1998 precipitation in inches. So it's a cell-by-cell operation. Every cell in the input grid is divided by 2.54 to give us the output grid in inches. And as we can with vector data, we can create strings of variables and operations, making an equation or a SQL statement that operates on multiple input grids, perhaps multiple operations or functions, and resulting in an output raster. So we often use these things for modeling things like hazard risks, indexes of various things. And in this particular case here, we're calculating runoff in centimeters based upon 4 different input rasters. precipitation, slope values, soil infiltration rates, and vegetation cover type. So the equation that someone has created here, remember to apply standard order of operations to it. Individually, we're taking values of precipitation, multiplying by 2, adding to that slope multiplied by 4, and dividing that by the sum, or the negative sum of erode subtracting veg cover. And that resulting value is, in this case, going to be an integer and displayed on the map as you see. So think about ways that if you're trying to come up with a complex relationship, just like we can with vector data, we can apply those same mathematical statistical principles as long as they're coded into our GIS software, and build an equation like this. It comes up with ratings, indices, various kinds of variables that are describing environmental conditions, which is quite often what we use raster data for, is landscape level environmental analyses. Typically, one of the more common things that you would do would be a site location analysis or hazard risk. But anyway, here's how we can use the simple operation of a map algebra and apply it to multiple inputs at the same time. Another thing that we can do here in ArcGIS and in many other types of GIS systems is we can take an input grid and convert it into an output using Boolean logic that will produce a raster that's filled with values of 1 or 0, where 1 is true, meets the condition that we queried of the data set. False means it did not meet that condition. So the output grid is filled only with 1s and 0s. This is something, if you apply these operations, these logical operators, Boolean operators, to a data set, you need to recall and remember to write down somewhere, record what it was that you did to create that condition. Because the only thing you're going to have in the output is going to be 1s and 0s. It's not going to be obvious to anyone else looking at that what you did. So, if we use this example here, elevation greater than 1200, typically that's going to be in meters. Our 1s will be the locations, the cells that meet the condition of elevation being greater than 1200. In this case, that's shown by the kind of bluish purple. The other second condition, slope less than 10. Okay, so 1s and 0s. This time the outputs 1 are green. 0 is kind of the pinkish, almost reddish tone. And we can make a more complex logical operator. Crown cover less than 70 and crown cover greater than 40. So that has to do with how much the trees are growing into each other and having overlapping branches, essentially. And so where the condition is true, again, green. Where it's false, the purple color. All right. So looking at those individual output rasters, you would have no idea what they mean unless someone has written down the operation that they used to create them, or they put it somehow into the name of the raster, which is going to be difficult because rasters must have shorter names than other data sets, or they won't be created. So anyway, here's how we can apply this idea of querying individual data sets and producing values that are conditional upon our input equation. So to drive that idea home, once again, Boolean operators, Boolean logic applied to a raster input grid, whatever that equation or query is going to produce values of true and false only, where 1 is true, 0 is false. So slope less than 10 degrees, again from the last slide. The green areas are true, meaning they only have values of 1. Every raster cell out there that is colored green has a value of 1. Every raster cell out there that has that pinkish color has a value of 0. Those are the only two values that are in the output. So we're reducing our input raster with its much richer range of values, and reducing it to, does it meet this particular condition or not? And this is something that we use in analyses later on at different types, and we'll go through that and see applications of Boolean rasters. So our Boolean operators, and, or, XOR, and not, are the ones that you're going to run into the most often. A and B means that it must meet both conditions in order to be true. That's the intersection. A or B is the same thing as a union. That means all of A or all of B can be true. A XOR B, XOR is exclusive OR, and this is the area that's either A, the area that may be B, both of those together, but where they intersect, that gets excluded. So that's why it's exclusive OR. It works like OR, but it excludes anything that's common between the two inputs. And A not B gets rid of anything that is coincident between the two, retaining everything that's A. Okay, so these are things, if you've had logic classes before, you've run into these in proofs, things like that, or perhaps in other math classes. So that's how these operators work. Okay, and you've been exposed to them before in vector data. They do slightly different things here in terms of how rasters get analyzed. So with our Boolean or logical operators, results of 1 are true, 0 is false. Let's go through and refine that just a little bit. With AND, both inputs must be true in order to produce a true result. And so this example here, the graphic is saying anything that's a positive number, or anything that's a number, is true. Ends are no data. Okay, so you can evaluate the three operations that are shown and or not using those ideas. Or that operator means that either input is true in order for it to be true. XOR works like OR, but again, exclusive OR. When both inputs are true, we're losing the intersected area that's common between them. Not reverses true and false. And the N is no data, or in our secondary textbook known as a null. So anything combining with a null or no data in ArcGIS results in no data. In other geographic information systems, other programs, that may not be the case. So always check your software manuals and help files and documentation to make sure you understand how that particular conceptual value is handled in other systems. So if you take a look at these and just examine them, if you have a secondary text, just open it up and look in the raster analysis chapter. Look through them, make sure you understand how they're working. So if you use these operators, you understand what the output should be, you can predict what the output should be, and you can check it to make sure that it did what it was supposed to do, as we should do with all of the output layers that we create anytime we do any kind of a GIS function. So some more examples showing these Boolean operators using the principles of true and false In our really simple input grids, A and B being either true and false values in each cell, A and B, we must have both of those conditions true in order to receive a true value, or 1 in the output raster. So evaluate those. You see that there's only one cell possible between the two inputs. A or B, the union, either of those can be true, and the output is true. So you can evaluate the two really simple input rasters to see how that works. And there's some little text over to the right, though. If you look through it, you'll see it matches up and explains what's happening between those different cells, values, true and false, combined with the AND operator, the OR operator. And again, the other two operators that we have, exclusive OR and NOT. So exclusive OR works like OR, but anything that is values of true with both inputs at the same time will result in false. So it excludes the common area, it excludes the intersected area, and that becomes false. A not B reverses things, acts like an erase function here with raster values. So, if you're not used to thinking about this kind of logic, these can be a little bit confusing, but this is how they work, and we use them in raster analyses quite often. Usually the first two will be used more often than the others. And an OR are far more common than XOR and NOT. But sometimes a analytical procedure will call for using these other two operators. So understand what they are, and they are explained out and diagrammed in our secondary text pretty well. So let's get down to what can we do with Boolean overlays when we have them. So we've created a few. Here's a real simple analysis. We had a precipitation layer, and we queried it to find areas that had greater than 60 centimeters precipitation. That's the ones in the figure on the left. The figure in the center, we queried an elevation grid, and we got all the values that were greater than 1,500 meters as 1, in this case green. The first one, they're blue. Okay, if we combine those using an AND operator, so think about Boolean logic, 1 and 1 is 1. So our output grid, all the areas that are common for 1, the intersection, are now what we're saying here is lodgepole pine habitat area. And all the places where we had zeros, both zeros from both input grids, or we had a 1 and a 0 from the input grid, the output is 0. Okay? So that's how this works. We're using Boolean logic at first to query these rasters to produce the grids of 1s and 0s, trues and false, for those conditions. And then we combine those conditions, and we get a restrictive idea of here are these cells in this study area that have both of the characteristics we're interested in. The precipitation is greater than 60 meters, and also the elevation is, or 60 centimeters, excuse me, and the elevation is greater than 1,500 meters. Both conditions are true in the output grid. Another way to think about Boolean AND is that it's essentially multiplication. Using the same example from the previous slide, we have the two input rasters of precipitation and elevation, trying to figure out where lodgepole habitat might be using only those two input rasters. So both conditions being true, 1 and 1 equals 1, that's the same thing as 1 times 1. 1 and 0 equals 0, 0 and 1 equals 0, 0 and 0 equals 0. All of those are multiplying by 0, essentially. So Boolean AND if you're using Boolean inputs, remember that what the result is going to be is essentially multiplication. So wherever you've got the Boolean and operator within a SQL statement analyzing different grids, it's going to act like a multiplication factor. All right, so that's just something to keep in mind. That's a benefit. It can also be kind of a hazard, depending on what you want your analysis to be in the end. If you use a Boolean AND in there somewhere, you're going to wind up with this multiplication result. Another way that we can combine the Boolean inputs, instead of using AND, what if we used just basic arithmetic and added them together? So we have inputs of 1 and 0 from the precipitation raster, 1 and 0 from the elevation raster. Our potential range of values in the output is 0 to 2. Okay, so what does that mean? We're essentially applying scores or ranks to each individual raster cell, where zeros indicate neither condition exists, 1 indicates one of the conditions exists, 2 indicates that both conditions exist. So lodgepole pine may do well in areas where the elevation is greater than 1,500 feet, and it may not do quite as well as it does where the precipitation is also greater than 60. So think of this as, that kind of a rating or an index, where the higher the value, the more likely it is you're going to find that particular, in this case, tree community in those cells that have the higher scores. It's more suitable for being habitat that tree species can thrive in. The 1, in this case, would be more marginal. So imagine if we were to combine 12 different input grids. We'd have a range of scores between 0, potentially 0 and 12. So there we'd have a larger range of very suitable habitat where the range's values are higher, grading into marginal or habitat where the values are lower, and then where the species couldn't possibly exist if it was 0. It's just not going to happen. You're not going to find it there. So this is something, it gives us an idea of the what habitat is, but it's a little bit more open to some of the gradations that occur in reality on the landscape, knowing that certain species can survive in conditions that are not optimal. They're not perfect. It can survive in areas where we're missing a little bit of some of the characteristics that it would prefer to have to thrive and survive.